Good. So, yeah. Okay, I think today we'll go through the, I mean, so far the yesterday's discussion, I mean, last time's discussion was operators acting on, I mean, not necessarily finite dimensional spaces, right? It could be also infinite dimensional spaces. But now we'll restrict ourselves to finite dimensional spaces. So the vector space which will, where the operators will act will be finite dimensional spaces. We already discussed in the beginning of the, I mean, the first week, we discussed something about finite dimensional spaces. But now let me just try to remind you because you might have forgotten about it. Okay, so S is a finite dimensional, space, vector space. And let's say I call the dimension as n. N is a dimension. N is a dimension. Okay. Then that means that you can choose a basis, and basis will consist of n linearly independent vectors, and I will just call them as I, where I goes from 1 up to n. So these are linearly independent, so it's a basis, n of them. So what it means is that any vector A I can expand as linear combinations of the basis vectors, right? And I will just denote them as AI, I. Okay? So this is an arbitrary vector, any vector. So for all A belonging to S, you can expand it in a linear combination. Again, I will be using whenever you see the same index appearing, it's a summation. So, I mean, many times I may not write this explicitly, but it's understood that whenever there is a repeated index, it's summed over. Okay. So this is the situation. Okay, now let's consider the set of linear operators. Should I discuss the change of basis? Yeah, maybe I should discuss already change of basis. Remember, this basis is not unique, right? I mean, you could choose another basis. There's nothing unique about this basis. You could choose another basis. So suppose there's another basis. Which I denote by I primes. Again, I goes from 1 up to n. So this is another basis. Then in this basis, again, I can expand A, the same vector, A, in this basis. Of course, in this new basis, the coefficients will be different in general. So I call those coefficients as A prime I prime, summed over I. Okay? I mean, this prime just means that it's a different basis. That's all. Now, you can ask the question, what is the relation between these numbers and those coefficients? There must be some relation, right? And the relation is coming, you can obtain the relation once you specify, say, the new basis vectors in terms of the old basis vectors, right? After all, you can expand each of these vectors in terms of linear combination of this basis vectors, right? And this is what we did. So expand the I prime vectors in terms of the old basis. Let me write it like this. This will be, again, I can write it as some R, some coefficients which I call R, Rji, J, summed over J. Yeah? I mean, these coefficients, so this is the summation. See, I'm just, forget this I index for the moment. I mean, any vector I can expand in terms of this basis vectors. So there's a summation over the J, right? But these coefficients will be different for different vectors, right? So this is just to indicate that these coefficients are different for different I's, different I primes. And you remember, I think this is one thing we proved, that if you think of this as a matrix, so write this matrix, so matrix R, let's define the matrix R as, so J labels the row and I labels the column. So that means we have R1, 1, R1, 2, R1n, and then R2, 1, etc. And finally Rn1. So I can arrange these, I mean, I and j run from 1 to n. So this fills out an n by n square matrix. Okay. Then the important point here was that this R, determinant of R, is not equal to 0. Right? That was a necessary condition. And the reason is easy to understand. I think I went through this proof of that, but I just remind you what was the reason. It was the reason was that, I mean, after all, I mean, here I expanded the new basis vectors as linear combinations of the old basis vectors. But I could have expanded the old basis vectors in terms of the new basis vectors, right? But in that process, the coefficients which will appear here will be the coefficients appearing in the inverse matrix, because that's an inverse map, right? So the inverse must exist, right? And the necessary condition for inverse to exist is the determinant of that matrix is not 0. Okay. So this is not 0. So R inverse exists. I mean, of course, R inverse exists. In fact, because this exists, that's why we said determinant of R is not 0. Okay. So in other words, what we are saying is that if I expand the old basis vectors in terms of new basis vectors, then the coefficients which will appear will be the coefficients appearing in this matrix, R inverse matrix. So this will be R inverse J prime. Okay, J going from 1 to n. So this is the inverse map. Okay. So given this, now I can, you see, relate A prime to A, right? I mean, A prime i's to A i's. Well, let's do that. So let's start from here. I can rewrite this as AI and express I in terms of the new basis. So then that becomes R inverse J prime. So now I have a double sum. First of all, there is a sum I going from 1 to n, and there is also a sum j going from 1 to n. I mean, this sum was already there, I sum, but now when you express I in terms of that, there's another sum. Now compare this expression to that expression. Okay? I mean, here's a dummy index, so let me just call it j, right? This is this is just I'm summing over j, so I can just use any label. That's just for convenience. So now just compare the two things. I mean, these two must be equal because it's the same vector, right? And then use the fact that all these j primes are linearly independent. So only way this can be equal to that is if the coefficient of each j prime, coefficient which appears in front of j prime, should be the same on the two sides. That follows from linear independence, right? So by comparing these two, we get to the relation A prime j is equal to summed over I, AI, let me write it like this, R inverse Ji AI. Right? This is the expression which relates A prime to A. I mean, this just involves exchanging the sum. So instead of first summing over j and then summing over I can first sum over I and then sum over j, right? So just exchange the sums. So this is j and I. And now look at this term inside, which is multiplying this is the coefficient which is multiplying j prime. So this has to be equal to A prime j. Right? So that's the idea. Okay, you can write it in the matrix language in a very convenient way if you arrange these A's and A primes and A's in a column vector, right? Then this is, you recognize this is just an ordinary matrix multiplication because J refers to the row, I refers to the column, right? And here I'm arranging it into a single column vectors. Then in the matrix language, it is simply, this is the same as A prime, thought of as a column vector, is R inverse times A, matrix multiplication now, where these A's and A primes are column vectors. Okay? A1, A2, A3, all the way up to AN column vector. So this is the basic transformation rule. So when I change the basis from one basis to another, the coefficients transform like that. This is the relation between the coefficients. Okay, this is just reminding you of what I had already discussed. Okay, now let us go back and let's look at the linear operators. So linear operators acting on finite dimensional spaces. Now what I will show is that any linear operator can be represented as an n by n matrix. Okay, any linear operator. And okay, so let me discuss that. Okay. Okay, first of all, let's see. Take, say, A is a linear operator acting on S. Acting on S. So now A acting on any vector, therefore, first of all, A acting on any vector will again be an element of S, right? So in particular, let's look at A acting on I. I is, of course, one of the vectors of S. So just apply. This again will be some vector of S, and therefore I should be able to expand it in the basis, in this basis. So this should be some linear combination of all these basis vectors, and I call these coefficients as A, J, again the same thing, Ji. Okay, so this is the summation. I mean, forget the I for the moment. Then this is just coefficients. But again, for different i's, these coefficients will be different in general, right? So to indicate that, I have put the label I here. Okay. So again, the summation is over G. I will try to keep writing the sum, but sometimes I may forget it. But then you should remember that whenever you see the same index appearing twice, I am summing over. Okay. So this is again, I can arrange it in a matrix form, right? J refers, again, J labels the row and I labels the column. So you see A I have written as this operator A I have written as a n by n matrix acting on the basis vectors, right? But now you see you can with this, once you define this, once you specify this n by n matrix, right? Then it uniquely determines that its action of the operator A on any vector of S. You see, at the moment so far I've only talked about its action on the basis vectors, right? But that's not enough. I need to specify its action on arbitrary vector, right? So how do you do that? So how one can get this? Let's say, take an arbitrary vector A. Well, this will have some AI I. Okay, I can expand it. Now, capital A acting on A. I can just see what it is. This is the same as A acting on this thing, some AI I, right? Now I use the fact that A is a linear operator. So that's crucial. So this word was crucial here, linear operator. So since it's linear operator, this is the same as sum over AI. AI's are numbers, remember? And this A will act on that, right? A acting on I. Okay. And this I know what it is. I mean, that's given there. So this is the same as AI, AJI, J. Summation over I and J, both going from 1 to n. Okay. So what we are seeing is that this action is entirely determined once you specify this n by n matrix, and of course its coefficient in that basis, right? And once again, you see you can write. So I mean, this vector, whatever it is, I can expand in the basis vectors. So it will be some coefficients. I don't know. Let's call it A tilde. It's, let's say J, right? After all, this will be some vector. I can expand it. It will have its own coefficient. I just call them A tilde. J equal to 1 to n. So this tells me what is A tilde J by comparing the two things. So the way it acts is simply, okay, so I think let me try to say, once you have chosen the basis vector, then the vector space S is isomorphic to a n column vector, right? Because any vector can be expressed in terms of these n numbers, right? So you can map this vector space S to the space of n column vector, right? I mean, one column with n entries. So it's completely isomorphic. Of course, we saw that when you change the basis, those numbers will transform, right? But nevertheless, this is basically isomorphic to a n column vector, right? Same way, the linear operator is isomorphic to a n by n matrix. And the way it is working is that its action is simply given by, again, in the matrix notation, you see, in the matrix notation, A tilde is nothing else but A times A, right? Where this A and A tilde are column vectors, and A is the n by n matrix. So this is the way so you see the A is completely, once you specify this n by n matrix, it completely uniquely fixes its action on every vector of S, right? So that's the reason why I'm saying that it's isomorphic. I mean, the linear operator is the same as n by n matrix once you choose a basis. Of course, if you change the basis, the operator will also transform. I mean, this n by n matrix will also transform. So let's see how it transforms. So let's say you have A acting on some basis I prime. We'll have some different coefficients. These are different basis vectors. It will have coefficients like let's call it A prime, Ji, J prime, right? This is now expanding in the new basis. It will have some different coefficients, not the same coefficient, but different coefficients in general. So that's why I put a prime there. Now we want to find the relation between this coefficients, primed matrix. I mean, this is a different n by n matrix compared to that in general, right? So we want to find now a relation between this and that. So how will we do this? Well, J prime. So this is the same as remember J prime was. So let's write it like this: A prime A prime Ji, or perhaps maybe. Yeah, let's try to write the relation between this and that. So first of all, I prime. I remember I prime was by definition Rij J summed over J, right? So let's see what is it. A I prime, therefore, is the same as A acting on that. But again, use the linearity property, then that's the same as sum J equal to 1 to n Rji, and then A acting on J, but that from this is A J K K, and again summation over K also. Right? But now I want to re-express, I mean, if I want to compare this guy with whatever appears here, you see I need to expand in the same new basis, right? Whereas here this is in the old basis. But I know how the old basis is related to new basis by R inverse now, right? So this is the same as K equal to 1 to n, J equal to 1 to n, and then so then you have Rji, Akij, and then I just express this. So this will be R inverse K, say L prime, right? I just express this K, this vector in terms of the old basis. So now I have a summation over L also. Okay. Now I can compare these two. Okay. I mean, here I put index J here, but there it is appearing L prime. So it is convenient to just rewrite J with the L, right? So I just write L here, this L, this is L, okay? And now we get the relation. So the conclusion therefore is from here, I can erase this part here. The relation between Li is equal to R inverse Lk Akj and Rji, summation over all the repeated index. So K and J are summed over. K and J both are going from 1 to n. I mean, L and I are not summed over. Right? Again, you can write it in the matrix language, right? Remember that this is the row, that's the column. This is the row, that is the column. And that's again the row column, right? So this is the standard matrix multiplication. So A prime as a matrix is simply R inverse times A times R. So this is how the linear operator transforms when you change from one basis to another basis. Okay. So note that this guy transforms with a R inverse, right? I mean, these A's were transforming with a R inverse. I mean, A prime was R inverse A, right? Objects which transform with the R inverse, I mean, this index, this I index is transformed. I mean, that I'm keeping this position of the index up for a particular reason, okay? Whenever the index appears up, this index are called contravariant index. Contravariant index, okay? So when the indices are up, this is our convention, but I've chosen this convention that I put the index up. I will always, the main point is that these indices transform with R inverse. This is the main point. So the indices which transform with R inverse are called contravariant indices, okay? And I will keep the convention that all those such indices I always keep up. It will be superscript, not subscript. So these indices that transform by R with R inverse are called contravariant, indices. Contravariant indices. Okay. So that's what. Whereas the indices which are down, those will transform with the R, not R inverse. I mean, in fact, you see that here there are the index which is up. You see that is transforming with R inverse. The index which is down is transforming with the R, right? Not R inverse, R. So those indices are called. So this will be the covariant indices, covariant, and this will be contravariant. Yeah.
What is the physical meaning of contravariant and covariant?
It's just, I mean, physical meaning. Perhaps maybe what I will do is I will try to write down. So, I mean, this was a R. R was transforming the linear operator. I mean, linear operator was transforming the R inverse and R. One index with R inverse, other index R. Now, you may ask, is there something which I can associate not with the linear operator, directly with the vector? Something which transforms as covariant, as a covariant index. Okay, I mean, so okay. Let me see how to say this. It's a difference between. Okay, one way to. Okay, let me first define that, and then I'll come back to. There is one way to think about it. In fact, it's a very good question, actually. So there is another quantity I can define. So given a vector A, I can define another quantity. Given a vector A, and let's assume that this vector space has a scalar product. So then in that case, I can define the dual vector A, right? This will be the dual vector, dual to A. This is a dual vector. Then I can define a quantity which I define like this, A with the basis vectors I, whatever basis vector I have chosen, right? So this I goes from 1 to n. So for each of these I, there will be some number. This will be some number, right? I call that as AI. Okay. This will transform with the R, not R inverse. Okay. And it's easy to see. So suppose I have chosen another basis now, I prime basis, and again I can compute this quantity, right? This will be not the same number, it will be some different numbers in general, right? Because the basis is different. So I call them as A prime I. Now I want to find the relation between this and that. Okay? So what will that be? Let's just express this I prime in terms of I. This new, and that is simply given by A with summed j going from 1 to n, R I j j. Now it's an R matrix is appearing, right? Because I prime is now expressed in terms of that. Once again, use the linearity property of the scalar product. So this is the same as R j I A j summed over j, right? And this is what we call AJ. So you see that this is simply R j I A j, and I put here like that AJ. summed over J. So now you see the, so now since I'm choosing the convention that this is the row and that is the column. So to write it as a matrix multiplication, I should think of these guys as a row vector. I should arrange these as a row vector, A1, A2, A3, etc. So once if you do that, then I can again write it in a matrix notation. So in this case, the equation would be simply A prime as a row vector now is equal to AR. Right? So we have defined, so associated with the given vector, you can define a contravariant object, which is just the coefficient in the linear combination, right? AI summed over I basis vector. So that was the contravariant index. This is not the, I'm not expanding this AI. I mean, these AIs are not the expansion coefficients, right? But it's a scalar product of I with A, right? And this guy is transformed in the with the R matrix, not R inverse matrix. Okay? So that is that's the one thing. Note, actually, one must say that just as these coefficients AI, which we defined A as summed over I mean, these coefficients uniquely specify the vector A, right? It's a unique. I mean, give me these numbers. This uniquely specifies a vector, and vice versa. Give me a vector, then there's a unique. These numbers are unique. That's why we said there's an isomorphism between the vector space and a column vector and column vector. Right? Actually, the same thing holds here. If you specify these numbers, then it uniquely specifies the vector A. Okay, you can prove that actually. That it uniquely specifies. But let me forget that for the moment, and let me come back to your question, which is one way to how to see this. The difference between these two is like, suppose I have some coordinates xi. I can make some transformations in the coordinates. I can go to xi prime, which is simply some ri rji xi. Suppose I consider linear transformation. Then dxi, if I consider small differentials, they will transform one way. Okay, I mean you can work it out. Just take the differential on both sides. So dx prime I simply is rji dxi, right? But d by dx, if I consider partial derivatives, d by dx prime I, that will transform differently, right? Because it will transform with the R inverse, right? Because, well, this is the same as dx, I mean, you can express in the usual partial derivatives, d by dxj, correct? This is the usual chain rule, right? You are familiar with this partial derivative, right?
Contravariant, like there is some sort of difference, and I think that I need that physical meaning. Yeah, I know the formal definition of covariant and contravariant, but I know the meaning.
I think it's just a statement that one object transforms as the coordinates themselves, right? And other object transforms as the kind of derivatives. I don't think there's more than that. It's just there are some objects which transform, I mean, different ways. That's all. I don't think there's anything more than that. Yeah. It's yeah. I don't know how to say this. This becomes particularly important when you talk about when you consider curved spaces and so on. But I don't want to go into that. I mean, yeah. Okay, maybe I shouldn't, because it's really got to do with general relativity and so on. Okay, but that will take me too far away from the. At the moment, I think it's sufficient to say there are different types of indices. Some indices which transform with the R matrix, other indices which transform with the R inverse matrix. Okay, And I will always use this convention that contravariant indices will be up, covariant will be down. So that is a consistent thing. Maybe we can discuss it privately, I mean, if you have this question. Because this is quite advanced question. I mean. Okay, now let me just say a few things about. Okay, so now let's go back to this various things that we discussed, right? For general operators, we said the left inverse, or this, you remember the last time's discussion that the inverse may exist or may not exist. Not necessarily that for every operator there is an inverse. And secondly, even if I mean there could be a left inverse, but may not have a right inverse, or vice versa. And then we proved various statements. But now let's specialize to the case of finite dimensional. In finite dimensions, we saw already that any linear operator is the same, can be identified with a n by n matrix. Okay. So question is now what is the inverse of a now we are all the problem is reduced to discussion about the properties of the matrices, square matrices, right? So the inverse would exist if the determinant is not 0. It's actually necessary and sufficient condition. Right? But let me just let me just review the notion of determinant of a matrix. I think some of you know it very well, but maybe some of you are not completely comfortable with the determinant. So let me just define the determinants. Determinant of a matrix, of a square matrix. This is defined only for a square matrix. Square matrix meaning that number of rows is equal to number of columns. Okay, let's so what is that? So let me just define. So let's take 2 by 2 as the simplest case. So this matrix will have some A, B, C, D, 4 elements, right? 2 rows and 2 columns. The determinant of this matrix is by definition simply A times this times that, A times D minus B times C. Okay, actually let me write it like this: A11, sorry, A12, A21, and A22. So first index is labeling the row, and the second index the column. In that case, this is simply A11, A22 minus A12, A21. Note the important point in these things. On the right hand side, there are these terms, but each row index appears once only. See, take this term. This row index is 1 here, then the other row index is not 1, it is 2. Same thing here. The row index is 1, this one is row index is 2. Look at the column index. Here it is 1, that is 2, and here it is 2 and 1. So they are all different. The row indices are all different, column indices are all different. And in fact, there is a relative sign. You see, what is the difference between these and that, right? The row index is the same, 1, 2, but column indexes I have exchanged it. And when I exchange the column index, I put a minus sign. Okay? Now let's take the example of the third, 3 by 3, just to get the this A11, A12, A13, A21, A22, A23, A31, A32, A33, right? Let's write down the determinant of that. How do you do this? you take, for example, one row, right? So you take the first element and then remove this row and column. Then what is left over is a 2 by 2 matrix, right? Then take the determinant of that. So this times the determinant of this submatrix, right? Okay, so let's write this down. So this is A11, and then you remove that row and column, and then what is left over? Determinant of that, but that's a 2 by 2 matrix. So we already know how to write the determinant of that. So it's A22, A33 minus A23, A32. Okay. Then I go to the next one in that row, but I give a minus sign now. So minus A12, so it's alternating plus and minus sign. So minus A12, and then once again, so you remove the row and the column in which this appears. Then what is left over is a 2 by 2 matrix consisting of this, 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 and take the determinant of that. So which is A21, A33, A21, A33 minus A23, A31. And finally, the last element here in the same row. So which is plus now because I alternate plus and minus sign. So this time it's plus A13. And then You want, again, you remove this row and column, then what is left over is this. Determinant is A21, A32, A21, A32 minus A22, A31. Okay? So this is the determinant. Once again, you notice the same phenomenon, that if you take any term, it will have, the row index will appear exactly, all the row indices will be different, you see, from each other. So 1, 2, 3. Similarly, 1, 2, 3 column index. This is true for every single term. So, and once again, you pick up a minus sign every time you exchange two indices. Two of the column indices you exchange, you get a minus sign. If you exchange twice, then you get plus. Right? All of this can be now written in a very compact form. And I will just try to, probably many of you have not seen in this language that I'm going to write down. Okay, so I will now define in general. First of all, in order to do that, I need to introduce, so for n by n matrix now, n by n matrix, arbitrary n. I need to introduce a particular tensor, which is called, which is called Levi-Civita tensor. Levi-Civita tensor. Okay, this is the symbol. I give the symbol here, epsilon. Let's say I1, I2, up to In. There are n indices here for the n by n. N indices. So in the n-dimensional space, when you're talking about n-dimensional space, after all, these matrices are going to act on a n-dimensional vector space. So for the n-dimensional vector space, I define a Levi-Civita index tensor. So this has a tensor with the n indices. And what is the property? That this is totally antisymmetric. Totally antisymmetric in all the indices. Okay. Which means if I exchange any two indices, then it becomes the minus of the original one. That's the property, totally antisymmetric. In particular, what it means is that if any two indices are equal here, it must be 0. Because if I exchange two equal indices, I should get a minus sign. So something is equal to minus of it's the same thing. The only thing is can be 0. It must be 0, right? So this implies, in particular, that if any two indices are equal, any two indices are equal, then it is 0. Then it vanishes. Remember, we are in an n-dimensional space, so each of these indices take value from 1 to n, right? They can only be between 1 and n, right? Okay. And what we are saying is that, so for example, if I take epsilon 1, 1, and then 2, 3, up to n minus 1, for example, this is 0. Because since it's totally antisymmetric, if I exchange 1 with 1, I mean, these two exchange, I should get the minus of the original thing, but that means it must be 0, right? So any two indices, they're equal to 0. So then all these indices, I mean, in order to get non-zero answer, I mean, for this to be non-zero, all these indices must be different from each other. But all of these guys are taking values from 1 to n, right? So the only way that can happen is if each of these numbers appear inside here, right? 1, 2, 3, not in the same sequence necessarily, right? But every number must appear once and only once, right? Okay. So this is the important point about this Levi-Civita symbol. But then I need to specify, I need to give some convention. So what we are saying is this is non-zero only if all these indices are different, which means between 1 and n, every integer appears somewhere, but only once. So now let's say, so for example, epsilon 1, 2, 3, up to n, this is not necessarily 0. It will be some number, right? Well, let's choose a convention that this is plus 1. We choose a convention. Then this uniquely fixes entirely everything, right? Because after all, every number has to appear. Every number has to appear somewhere here. So I can always obtain it starting from here by permuting, right? Suitable number of times, right? If you arrive at it by even number of permutation, it remains plus. And if you arrive by odd number of permutations, you get a minus, right? it fixes completely. So for example, epsilon say 2, 1, 3, I keep the remaining guys the same, but just exchange the first two. This will be -1, right? But if I exchange, let's say epsilon 2, 3, 1 up to n, I mean rest of the things are the same. I don't change. Rest of the numbers I don't change. This is still again +1 because this can be obtained by exchanging these two, right? So this should be minus of that. So this is minus, that's plus. So this one is obtained by two permutations starting from here. First you exchange these two, then you exchange that two, right? So there is a notion of odd number of permutations and even number of permutations. So any ordering of 1, 2, 3, 4 all the way up to n, if it is obtained from this standard ordering by odd number of permutation, it will be minus. If you arrive at it by even number of permutation, it's plus. So it uniquely fixes completely, right? This is the important point. Actually, this was a Levi-Civita symbol, but you see that this argument goes for any tensor which is totally antisymmetric. For a totally antisymmetric tensor, first of all, if any two indices are equal, it is 0. So only possibility is if all the indices are different, right? But then, if you tell me what is the value of this guy, I mean, forget the epsilon. Suppose it's any tensor, some tensor which is totally antisymmetric, okay? Then you just have to tell me what is this number. Once I tell you what is that number, then everything else is fixed by just the signs, right? You understand? I mean, suppose it was not +1, but I mean, suppose there is another tensor. Let me just call it A or T, another tensor, which I know is totally antisymmetric. I mean, which satisfies the condition that this is totally antisymmetric. Okay, then so totally antisymmetric tensor. Okay, then of course any two indices equal, which means it's 0, right? So it has to be all different. So each integer must appear from 1 up to n. So then I just need to specify what is this value, 1, 2, 3 up to n in this order. It will be some number. I don't know, whatever. Let me call it something. I don't know, alpha. Suppose this number. Then this uniquely tells me everything else because any other ordering I can obtain by even or odd permutation. So it will be just plus or minus alpha, right? What it means is that this is proportional to Levi-Civita index, right? So what we are saying is that this implies that any totally antisymmetric tensor is proportional to epsilon, and in fact in this case it's simply alpha times epsilon I1 up to In. Because this by convention I have chosen to be +1. For some other tensor, if this happened to be alpha, and I know this is totally antisymmetric, then this must be proportional to epsilon with a proportionality constant alpha. Okay. So this is a very important tensor. I mean, it's using this tensor now we can write down a formula for the determinant in a compact way, right? Because that procedure that we defined becomes very cumbersome. I mean, it's even difficult to write in a compact form a formula for determinant for n by n, right? Whereas in this, with using this tensor, we write down a very compact form. So let me write this down. Matrix. Can I erase this part now? Only thing is this just set a convention. I chose it to be +1. Then everything else is fixed. Okay. So we define the determinant. So first of all, let's see. Yeah. So this let's consider this object epsilon, say J1 or let's say I1, I2 up to In times. So there's a matrix, a square matrix. So I write it as I1 J1 A I2 J2 times A In Jn. Consider this combination. Once again, repeated indices are summed over. So repeated indices are i's, I1, I2. J's are fixed. Okay. So this summation over all I1, I2 up to In, each of them going from 1 to n. So there are n sums here. So consider this object. First of all, notice that whatever this object is, it is totally antisymmetric in the j's. J's are the free indices, remember. Okay. Why is it totally antisymmetric? Well, let's exchange. Suppose I consider the situation where I just exchange J1 and J2. So this guy is J2, and that one is J1. And everything else, I don't touch anything. So this is I3, J3, A, I, and Jn. Consider this situation. I mean this case. The same with the epsilon. Epsilon I1, I2, I3 up to In. And with the summation here. Well, this is the same. I mean, after all, i's are a dummy indices, right? So I can call this as I1, and that as I2, right? So let's call that. Let's change this to I1, this to I2, so that this is the same as that, right? But then I should change also here, right? So this becomes I2, and that becomes I1. Rest of them remain unchanged. Okay. So now you see this part has become the same as that part, right? However, this epsilon is not the same as that. But this I know that is totally antisymmetric, so I can exchange I1 and I2, but that will pick up a minus sign, right? Because of the epsilon property of epsilon. So that tells me that this object, whatever that object is, I mean, let's call this object as some, I don't know, T. It has free indices, this, right? J1, J2 up to Jn. Right? It will be something which will depend on these indices. But this argument says that this is totally antisymmetric in these indices. This tensor T is totally antisymmetric in these indices, right? So therefore, from the previous discussion, this must be proportional to epsilon, right? So what we are saying is that this guy is going to be proportional to epsilon, and the proportionality constant is called the determinant of A. Okay, so let me first write down. I know that this is going to be proportional to that because of the fact that I have already proven that this is totally antisymmetric, right? So it will be some number times that. That number is what is called the determinant of A. So this is the definition of determinant of A. Okay? This is the definition. To show to you that this in fact gives you the same answer as the usual determinant, let's just check that. For the 2 by 2 matrix, let's say, because otherwise to write it's too long. So for 2 by 2 matrix, what we are saying is that this is the same as for 2 by 2, so n equal to 2. So there are only 2 indices now here, right? So this is epsilon 1 2, a1 say, let's leave it as J1, a2 J2, right? Plus epsilon 2 1, a2 J1, a1 J2, right? But epsilon 2 1 is this. This is plus 1 and that's minus 1. So this is same as a1 J1, a2 J2 minus a2 J1, a1 J2, right? Okay. Now you see, if J1 is equal to J2, this is surely 0, right? Because this is suppose J1 equal to J2 equal to J, let's say. So this becomes A1J times A2J and minus A1J times A2J, two things cancel. So they have to be different. So let's take the 2 cases. So only way it can be different is, say, if this is 1, that is 2, or this is 2 and that's 1, right? So let's consider the case where J1 and J2 is equal to 1 and 2, right? Other possibility is 2, 1. I mean, by this notation means that the first entry is equal to that, second one is equal to that. In this case, you get, this is simply A11, A22 minus A21, A22. But that you recognize as the determinant of a 2 by 2 matrix, right? This is determinant of A. Right? Now take the other situation, say J1 and J2 are 2, 1. So J1 is 2, and so in this case, you get A1 2, right? J1 is 2, J2 is 1. So this is A2 1 minus A2 2, A1 1. But that is minus determinant of A. Because determinant of A is, you see, this minus that. So this is just a minus of the determinant of A. So indeed, you see that in this case, this is nothing else but epsilon J1 J2 times determinant of A. Right? This is now a general formula. This is, you see, this is a very compact expression, right? And it's a very powerful formula because all the nice properties of determinant you can prove in 2 lines. If you try to use that original definition of determinant and try to prove various properties of determinant, it's cumbersome. I mean, really, it can fill up pages after pages, you know. Whereas here, really 2-3 lines you can prove everything, all the nice properties of determinant. Yeah.
Where you are coming from, A1, J1, A2, J2, minus A2, J1,
Yeah.
A1, J2. Why is it that this other one must come to be A2, 2?
Sorry, which one? Maybe I made a mistake. Let's see. What did I do? Epsilon 1, 2, epsilon 2, 1. Yeah, so this is from here to here, it's fine, right? You agree from here to here? I mean, I'm just writing the formula epsilon I1, J1, I1, I2. This same formula, A I1, J1, A I2, J2, summed over I1, I2, right? So when the 2 are equal, of course, it is 0. So the only possibility is epsilon 1, 2 or epsilon 2, 1, right? So for these 2 cases, these 2 terms. So I just rewrote, I mean, using the fact that epsilon 1, 2 is plus 1 and epsilon 2, 1 is minus 1. So the first one is simply A1, J1, A2, J2. Where the second one is minus A2, J1, A1, J2. Right? So this is just that, where I just use the fact that this is plus 1 and that is minus 1. Right? Now, first statement we made was that, well, it's already from here it's obvious that if I exchange J1 and J2, it's minus, right? I mean, when you exchange, if I exchange J1 and J2, then you get, so you see if I exchange J1 and J2, you get here A1, J2, A2, J1, exchange J1 and J2, and here you get minus A2, J2, A1, J1, right? But this is the minus of that because you see the second term is the same as the first term, right? This is A2, J2, that's that, times A1, J1. So the second term is the same as the first term, and here the first term is the same as second term up to a sign. Here it's a minus sign, this was a plus sign, and here's a plus sign, that's a minus sign. So when you exchange J1 and J2, it's antisymmetric, right? So whatever this is, it's antisymmetric in J1 and J2. So all I need to check is, so when J1 is equal to J2, it has to be 0, right? Because it's antisymmetric. So all I need to check is what happens when J1 is equal to 1 and J2 equal to 2, right? And when I do that, this is the same as that, right? I mean, J1 is 1, J2 is 2, and here is J1 is 1, J2 is 2. But this is the determinant of a 2 by 2 matrix, right? I mean, if you remember the A1, 1, A1, 2, A2, 1, A2, 2, the determinant is this times that minus this times that, which is this. Okay.
So this one here should be A2, J2, not.
Have I made a mistake? No. Sorry, this is 1. That's a mistake. Yeah, this is A1, 2. Yeah, correct. Yeah. This is A1, 2. Yeah, here it was 1, 2. Right. Yeah, so this is the determinant A. Okay. So this is a very compact formula for this. So let me just write this explicitly here. I mean, just rewrite this. So this is, we are saying, this is a definition, determinant of A times epsilon J1, J2, Jn. In particular, what it means, determinant of A, I mean, just take J1, J2 in the sequence 1, 2, 3 up to n, right? Then this is just simply 1, right? So what we are saying, determinant of A, therefore, is simply epsilon I1 up to In, A I1, 1, A I2, 2, all the way up to A I n, n. I just took J1 equal to 1, J2 equal to 2, Jn equal to n from this formula and use the fact that that epsilon is 1. So you just get this formula. The summation, all the repeated indices summed over. Okay, now just to show to you how useful this formula is, you remember some of the properties of determinant. I mean, determinant, to do the determinant, you can either choose a row and open up like that, or you can choose a column, open it up like that, right? The different differences between these two is that here you see I chose this epsilon, the indices here, I contracted with the row indices here, keeping the, or look here, I mean, yeah, here I contracted with the row indices. Column indices I kept fixed, right? So that is one way of opening it up. I mean, one can work it out whether it's row or column, right? But if you do other way around, if you keep the row indices fixed and contract epsilon indices with the column, that will be opening the other way. But that's immediately obvious, I mean, because if suppose I had, in this formula, suppose I had put, instead of contracting with the row indices, suppose I had contracted with the column indices. Answer will be again the same. It's obvious, because the result is again going to be proportional to the epsilon of the free indices, right? And then you just take to find the proportionality constant. Again, you see you either fix 1, 2, 3 in the sequence, and you find it the same answer. Okay. So that is immediately obvious. Slightly more complicated and which are very, very useful properties of determinant is that if so okay, so let's see. Suppose I take a matrix A, which is of the following form. I mean, let's say A11, A12, A1n, A21, A22, A2n, etc. But suppose that this row was proportional to this row. Okay, so let's suppose this row. So in other words, A11j is equal to some number alpha times A2j for each j, for all j. So this is alpha times that. This is alpha times that, and so on. Just to take this case, I mean, as an example. Then the determinant of A is 0. Right? Why? Because let's see. Maybe okay. Let me do the following other way, because I've written the formula in this way. So let me take suppose the first column is alpha times second column. So in other words, it's I1 is I2. So the first column. So this is alpha times that. This is alpha times that, and so on. So the first column is alpha times that. Then just let's apply that here. So what we get here is so I1 up to In, and here I use the fact that I11 is the same as alpha times I12, I12. So you get alpha here, and here you get I12, and then I22, and the remaining guys are the same. Nothing happens, right? But this is 0. Why? Because these two indices are the same, but I know if I exchange I1 and I2, it's antisymmetric, right? Because of this epsilon. So the two terms will cancel. So you get a 0 answer, right? So in such cases, determinant of A is 0. More generally, if say the first column was a linear combination of the other columns, again it is 0. So suppose I1 was some linear combination, alpha say j, a I j, for j going from 2 to n. So the first column is a linear combination of this. Again, determinant of A is 0. For the same reason, you substitute now. Now instead of this, it will become alpha j, I1j, summed over j going from 2 to n. You see, in each of this sum, this j is going to be equal to one of the other indices which appears there, because here the remaining guys are going from 2. I mean, the next one is a I3 to 3 and so on, right? So all these different indices, 2, 3, the column indices 2, 3 up to n appear here, right? So this j has to be equal to one of these indices for all this j in the range between 2 and n. Right? And again, then you use the I1 and the antisymmetry in that to show that this is 0. Is that clear? I mean, in the same way that I did here. Right? I mean, say for example, take the j equal to 3 term. I mean, here that there are so many terms, right? But I'm saying that each of these terms vanishes. Take for example j equal to 3 term. Then there is a I3 3, and so j equal to 3. You have I1 3, I3 3. Huh? Again, this is totally antisymmetric. So I1 and I3 is also antisymmetric. So again, it cancels. The two, when you sum it up, it cancels. So this is the very important property of determinant, right? The determinant vanishes if any row or any column is a linear combination of other columns, or equivalently any row. I mean, as I said, it doesn't matter whether you contract the epsilon indices with the column or row. It doesn't matter. So that's the main statement of determinant, that if any row or column is linear combination of other rows or columns, then determinant vanishes. Okay, this idea. In fact, it's actually other way around also, but I'm not going to prove that. That if the determinant is not equal to 0, then necessarily all the rows must be linearly independent of each other, and similarly all the columns must be linearly independent of each other. Okay, this goes both ways. I mean, it's a very important statement of determinant. Okay, then there is another property. In fact, you remember that in computing actually determinants, a very convenient way of doing is start taking linear combinations of them to simplify. So you start taking linear combinations to set some of these coefficients to 0, as many coefficients as you can to set to 0, right? Because then the calculation becomes easy. So why is that true? Why is it okay to just take linear combination? Is because of that reason. When you take linear combinations, determinant doesn't change. This is the reason. Okay. Then there is another very important property, that the determinant of the product of matrices, two say n by n matrices, is equal to the product of determinants of the matrices. This you must have seen it many times. The determinant of A times B, so each of them is an n by n matrix. This and this both are A and B are n by n matrices, square matrices. Then this is the same as determinant of A times determinant of B. Right? If you try to see the proof of this using the old way of defining determinant, it fills up pages, But with this formula, it becomes immediately obvious. So let's try to work it out. So this by definition, so let's consider this A. This by definition is epsilon I1 up to In. A times B is some matrix, it's some n by n matrix, so I just call that matrix here. I1 1, A times B, the I1 1 component of that, I2 2, all the way up to A dot B, In n, right? But now let's use what is this quantity? This this comes from the matrix multiplication, right? So let's write that down. So this is I1 up to In. Sorry, there is a summation, but all this I indices are summed over. And then here you have A, I1, say J1, B, J1, 1, right? This is the I1 1 component of this matrix multiplication. I have to sum over J1. This is the column, that's the row. Okay. Again, shall I just, okay, let me write sum J1. That's the first term. Then here you have second, here again, sum A, I2, J2, B, J2, 2, J2 is summed over, and so on. A, In, Jn, B, Jn, n, Jn is summed over. Okay. Now take all these sums outside, so let's put all the sums outside here. So here there are all the i's and j's, I1 up to In and J1 up to Jn. They're all summed over. Okay. Now use this thing. Now let's look at this. keep the B as it is, don't think about the B, look at just the A part. So here you have epsilon I1 up to In, A I1 J1, A I2 J2, A In Jn. So that is what? That is what we said. This is equal to determinant of A times epsilon J1, J2 up to Jn, right? Times, so you see here I have summed over I1 up to In, right? So what is the remaining sums are simply J's, J1 up to Jn. I have to sum over. And then whatever is left over. So this is Bj11, Bj22, Bjn. But this is the determinant of B, right? So this way we have proven this is equal to determinant of A was here times determinant of B. So you see there's two-line proof using the properties of epsilon. It's quite. So what I did, I used the definition of determinant of. This is some matrix, call it C. A times B is some C. Determinant of C is, I just use this thing, is epsilon I1 up to In, C I1 1, C I2 2, etc. Right? Okay. Now I use after all, C is a matrix multiplication of A times B. And this is the element I1th row and 1 first column, right? Element. That is by definition this. I just use the matrix multiplication rule. Is A I1 J1, B J1 1. I1 is the row, 1 is the column, right? And similarly, this guy I2 J2, J2 2, In Jn, Jn. All these J's are summed over. J1, J2, these are all summed over. So I put them out here. Okay. Now focus on this part. Keep the B as it is. So maybe I should just write it a little bit more. One more line. I should write it to make it more obvious. So this I write it in the following way. I will sum over J's later. First I will sum over I's. So I write it like this, J1 up to Jn. And then inside here, I sum I1 up to In of these quantities. After all, this is a product. This times that times that times that is a multiplication, right? Inside the sum. So I put all the A's together. So here you have epsilon I1 up to In. And then you have A I1 J1, A I2 J2, all the way up to A In Jn. Okay? But I still have the remaining, these B's are still there. So B J11, B J22, up to B Jnn. Right? Okay. Now look at the focus on this thing inside the bracket. That is nothing else. I mean, this is what I said, that this object is totally antisymmetric in J's. See, J's are free indices here, right? I'm only summing over I's now. So this is totally antisymmetric in J, so it must be proportional to epsilon J1, J2, Jn. And the proportionality constant is by definition determinant of A, right? So that's what I wrote here. Determinant of A times epsilon J1, J2, Jn, and then the remaining objects which are there. And I still have the summation over J's. And this by definition is determinant of B. So it becomes determinant of A times determinant of B. Right? Okay. Right. So, and finally, okay. So this determinant is fine, but now I need to define. Let me write down also the inverse matrix, right? So first of all, the inverse exists if and only if determinant is not 0, right? Okay, so let's try to prove that. So can I erase all this now? By the way, these are not in the book, because in this book it's assumed the determinant is already, everyone knows the determinant. In fact, you all know it, but probably not in this language, in this epsilon with a Levi-Civita. But I'm introducing it because it becomes very easy to prove everything. No? And also this appears in the later on, I mean, this epsilon tensor appears in many places, so it's good to see it. So, but it is not included in the notes. So perhaps you should take the notes. I mean, this part. Okay, first of all, let's say, suppose there's a matrix A, and let's say A inverse exists. Suppose A inverse exists. Huh? Okay, so then I can take the A inverse. This is identity, right? Now, okay, I use the 1 n by this n by n identity matrix. So that's the definition of A inverse. Well, then let's take determinant of both sides. Determinant of this is simply the product of determinants. So determinant A inverse times determinant of A, right? And that's equal to determinant of 1, which is 1, right? So it's clear determinant of A cannot be 0, otherwise this equation will not be consistent, right? So this implies that neither determinant of A is 0, nor determinant of course A inverse 0, right? So this way is fine. So what this says that if A inverse exists, then necessarily determinant of A is not 0, right? Now, how to prove that if determinant of A is not 0, A inverse exists, right? We want to prove other way around. So the proof is by explicit construction. I mean, we'll just explicitly write down what is the A inverse if determinant is not 0. So let me define a matrix. Let's call it A tilde. Before that, I should tell you some nice properties of epsilon. Some nice property. Then because I need it to show this. Okay. So the property is following. Suppose I take say I1, I2 up to In, and epsilon say J1. So let me write like this: In minus 1, and then say just I, and J1 up to Jn minus 1, and then I, and sum over I. So these indices are free indices. I1 up to In minus 1 and J1 up to Jn minus 1 are free indices. Only the I is being summed over. The last index is being, I mean, any one of the indexes is being summed over. So in this case, I just put it to be last index. Okay. Now there is a nice formula for that, and that formula is simply, it is delta I1 J1. Delta is a Kronecker delta. This is a Kronecker delta. I2 J2 delta In Jn. Okay, and then plus or minus all the permutations. So keep the positions of the i's fixed. Then just permute the j's. Okay. So for example, then another term would be just exchange J1 and J2, keeping I1, I2 fixed. Right. So there will be another term which will be minus delta I1 J2, delta I2 J1, and keep all the remaining terms the same, I3 J3, etc. Right. And then, so take all the permutations with this way, with a minus sign for the odd permutations, plus sign for the even permutations. Okay. That is the answer of this thing. That the fact that you need to do this is clear, because after all, these guys, the j's satisfy that property anyway. So whatever the right hand side is must be such that when you exchange these indices, it should be plus or minus depending on whether it's a odd or even permutations, right? So this is what that has to be there. Now, how do you see this? Okay, so I mean, say I is summed over, right? So I can be equal to 1, I can be equal to 2, I can be equal to n, all the way up to n, right? So if I is 1, suppose I is 1, then these indices are necessarily different from 1, right? So they will go from 2 up to n, 2 up to n, right? In different orders, doesn't matter, but all the indices must appear 2, 3 up to n, somewhere inside here, right? Similarly, since this is I is 1, this is also 1, right? So again, these indices must be between 2 and n, right? In different orders. So what we are saying is that certainly one of these indices must be equal to one of the index there, but in different order, not necessarily the same order, right? So every index here must be equal to some index here, and that's what this is saying, right? I mean, this says that I1 is equal to J1, I2 equal to J2, right? Otherwise it is 0, that is, huh? Otherwise the answer is 0, right? So that's what this is saying. I mean, so the non-zero terms are only this, and then the ordering is just because this already satisfies that property of a total antisymmetry, right? So that is exactly the statement. This is the statement here. For example, let's say suppose this was 1, 2, 3 in this order. Suppose it was I1. So we are looking at this 1, 2 up to n minus 1, and then I. And then here you have epsilon 1, 2, n minus 1, I. So which means I1 is equal to 1, I2 equal to 2, I n minus 1 is n minus 1. And similarly, J1 equal to 1, J2 equal to 2, and Jn minus 1 is equal to n minus 1. And I'm summing over I. Now look at this. I mean, the only value, I mean, I is to be summed from 1 to n, right? But the first n minus 1 terms vanish, because then this I will be equal to one of these terms, right? So that will not contribute. So the only term which will contribute is when I is equal to n, right? So this is n and that is n. In that case, each of them is plus 1. So product is plus 1. That's it. And that is what this term is giving. Because in this case, you see I1 is 1, J1 is 1. So I2 is 1, J2 is 2. So this is the term which contributes. Everything else will vanish. So this is a way to check. But this is a general formula. Okay. You can, okay, here I contracted only one index. This is called contracting index. I summed over only one, contracted and summed over only one index. But you can sum over, you can contract many indices, right? In particular, a formula which you can get for when you contract n minus 1 of these indices and keep only one free index from each side. Okay, so consider this thing now. So summed over say I2 up to In of epsilon say I, I2 up to In, and times epsilon say j, I2 up to In. So you see the free index is I and j. All these remaining n minus 1 indices are summed over. They are contracted, I mean the same index, I2, I2, I3, I3. This is going to be proportional to delta ij, that's clear, right? Because for the same reason, I mean, all these indices are different from each other and different from I, but these indices are the same here. So whatever happens to be I, the j must be also the same, right? So for example, suppose these indices were 2, 3 up to n. Then this also is 2, 3 up to n. Then I must be 1 and j must be 1. So I has to be equal to j. So it's going to be proportional to delta ij, but you can verify that the proportionality constant is factorial n minus 1. Okay. Why? Because, I mean, let's take, suppose I is equal to 1, j is equal to 1. Then this can be from 2 to n, right? But all possible orderings. So there are n minus 1 objects from 2 up to n, right? And these numbers you can, in different permutation group of n minus 1 elements, right? That is the order of the permutation group is factorial n minus 1. That's what it is. Okay? So this is the formula that you get. Okay. So having said about this, some nice properties of the products of epsilon and contractions and so on, I can now define a matrix A tilde. Okay, this I will define epsilon, let's say I1, I2, In, epsilon J1, J2 up to Jn, and then A, I2, J2. So I'm keeping I1 and J1 as free index. Other indices I'll sum over. A, I3, J3, all the way up to A, I and Jn. So we are summing this over I2, In summed over, and similarly J2 up to Jn I'm summing over, but not I1 and J1. I1 and Jn are free. So the right hand side has to have a free index, and let me call it J1 I1. Okay. So I have exchanged here. And this is the definition. Then I divide by determinant of A and a factorial n minus 1. Okay. So this is I just constructed a matrix. I just constructed a matrix A tilde whose j1th row and I1th column element is this. Right? I just define it. I can do that because I'm assuming determinant of A is not 0. See, now what I want to prove, if determinant of A is not 0, A inverse exists, right? So since it is not 0, by assumption, I can divide by determinant of A. Right? So this, what I claim is that this is the inverse of A. Actually, both left inverse and right inverse is the same matrix, A tilde. So notice that, yeah, here there is a, yeah, okay. So let's try to prove that. So I want to prove that this times A tilde times A is identity, right? So let's try to. So we want to prove that A tilde times A is identity. So let's multiply that. So what is that? This is, so if I look at the, let's look at A tilde times A and the j1th row and let's say, I don't know, let's call it k1th column. I want to construct this, I want to write this down. This by definition is A tilde j1 I1 A I1 k1, matrix multiplication rule, right? Where I1 is being summed over. Okay, so A tilde is there, so let's write this down. This is, so I have a summation. Okay, I will define the summations later, but let's write this down. So epsilon I1, I2 up to IN, A, so let me write A, I2, J2, A, I3, J3, up to A, IN, JN. Divided by factorial n minus, so there are two epsilons. Okay, epsilon I1 up to IN, epsilon J1 up to Jn, okay, and then factorial n minus 1 and determinant of A. That is the A tilde, that's the A tilde J1 I1 element, right? Now I have to multiply that to A I1 K1. So let me multiply here A I1 K1. So now I have to sum over I1 also. So what is the sum? Sum over all the I indices, I1 up to IN, because anyway, from I2 up to IN was summed over here already, but now I have to sum over I1 also. So sum over all I1 to IN, but the sum over J is only from J2 to Jn, not the J1. J1 is not summed over. J1 is a free index. And similarly, K1 is a free index. Okay. So this is what it is. So let me not erase this part because I need this formula actually. Okay. Now look at this term here. Forget the, first I sum over i's. I mean all the i's. Remember all the i's are summed over. Keep the j's separate and look at all this term. Right? This is going to be totally antisymmetric in the free indices k1, j2, j3, jn, right? And this is proportional to epsilon. So this is proportional to epsilon k1, j2, j3 up to jn. This combination. So so first sum over i's. First sum over all the i's, I1, I2 up to in. In this, I mean I have two sums, j's and I. So keep the j's fixed and first do the sum over I. After doing that, then we will do the sum over j's. So this is going to be proportional to that, and the proportionality constant is determinant of A, right? So that determinant of A will cancel with this determinant of A, so that goes out, and then what is left over is this times epsilon I1, no sorry J1, J1, J2 up to Jn, right? This epsilon, and I now still have the sum over J2 up to Jn. And a 1 over factorial n minus 1. Okay. But now use this identity. You see here exactly I have, I mean from the second to the last index I have summed over, right? That's what is happening. From the second to the last index I have summed over, contracted and summed over. Then this is going to be simply delta k1 j1, right? I mean using this formula, that factorial n minus 1 cancels. That's the reason for factorial n minus 1 down, to cancel that. So what we have proven here is that what did we calculate actually? What we calculated here was simply the A tilde A and K1 J, J1 K1 term here. And we proved that that is equal to that. That's exactly the, I mean, this is identity matrix, right? So we are saying this is diagonal and it's equal to 1. The diagonal elements are all 1, right? So we have proven that A tilde times A is identity. You can also prove that A times A tilde is also identity. Okay? In fact, it's the same. I mean, I won't go through that. It's exactly the same type of computation. So this here is a construction, explicit construction of the inverse matrix. So we are saying A tilde is in fact A inverse, where A tilde is defined here. Explicit construction. Okay. So now what I should say. Okay. Is everything clear? I mean, any question on this so far? Okay. So now, what should I? Yeah, I think. What should I say? You remember I mentioned to you that the covariant objects, covariant quantities that we defined, AI is equal to AI, right? That this uniquely specifies a vector A. Okay. Now, how can one prove that? Well, remember A itself we can expand the basis, and those were the contravariant objects. This is how we defined. There's a summation here. Okay. So this of course this uniquely determines the vector A. Now we want to show that this also uniquely determines this vector A. Okay. So let's write this down. So what is the dual vector here of this guy? The dual vector is, remember when you take the dual, so you get the dual of that, but you have to take the complex conjugate of this, right? So this is A bar I and the dual vectors of the I. Okay. Actually, let me put here J. I mean, because I'm going to take. So this is dummy. Dummy index you can always change. You can choose your label, whatever label you want to choose. Summation over J. So let's compute now what is AI, and using this form of the dual. So we find this implies that AI is equal to the dual, which is that. So you get here A bar J summed over J, and then Ji. Okay. So what we want to prove is that if I give you these numbers, then I can determine these numbers, because once I know these numbers, then I know these numbers. I just have to take the complex conjugate, and that uniquely tells me what is the vector, right? So what we want to do is that so this equation expresses AI as combinations of A bar J's, right? But I want to solve the other way around. I want to solve for this in terms of that, right? So here's what we have is a system of linear equation, right? System of linear equations. So think of these as unknown quantities. Say these are given to you. This I choose some numbers. These are unknown quantities. Okay. So you want to solve for these unknown quantities. It's linear equations. How many linear equations are there? There are precisely I is the free index here, right? N linear equations, because I goes from 1 to n, right? And the number of unknowns is also n. So you have n linear equations for n unknown quantities, and it's inhomogeneous equation because this side is not 0, right? So it's a n linear inhomogeneous equations for n unknown quantities. n unknown quantities. Okay. So let me give a name to this. Let's call this guy as give a name. So call this as some Mij. Okay. This depends on I and j, right? It will be some numbers. So those numbers I just write as Mij. Then this equation I can write it in the matrix language. M times A bar, M times A bar is this A. I don't know, what shall I write? So let me write explicitly. A1, A2 up to AN. So this is this side. Okay. And here, what I mean by this matrix is simply A bar, I write it like A bar 1, A bar 2 up to A bar n. And then this matrix M. Okay. So M11, M12, M21. Okay. This matrix, I just I mean this. Now there's a summation here, right? I mean, you see the J is a column, and I'm summing over J, right? That's a usual matrix multiplication. The column is multiplied with the rows here, right? And so I have to sum over that. So this equation can be rewritten in the matrix language like this. So if now the inverse of this matrix exists, then the solution exists, because just you. So this the matrix equation is M A bar equal to A. I don't know, what shall I? Not this A. You see, this is I mean this upper index, that's lower index. Huh? So these are two different quantities. I don't know. Let me just call it B. This guy has some B. Huh? Not to confuse these are two different objects. These are given to you, and I want to compute that. So I just call this B. So I mean the solution, if the M inverse existed, then clearly A bar is simply M inverse B. Right? You just multiply by M inverse from the left. Right? So the whole issue of this, whether you can determine these guys in terms of that, is boils down to whether this matrix has an inverse or not. Okay. So now its inverse will exist if the determinant of this matrix is not 0, as we have just seen before. So what we need to prove is the determinant of this matrix is not 0. Right? That's what we need to prove. Okay. So in other words, this viewed as a matrix, its determinant is not 0. That's what we need to prove it. So let's see. So let's assume the contrary. Let's assume we'll prove it by contradiction. Okay. Let's assume that this is 0. Okay. So prove by contradiction. Okay. So suppose, so we let the determinant of M be equal to 0. But that means that, say, not all the rows or not all the columns can be, I mean the columns are linearly dependent on each other, or rows are linearly dependent on each other, right? So this would imply that there exists some coefficient Ci. So let's say Mij Ci. This implies that there exist non-trivial Ci's, meaning that not all of them are 0, such that Ci Mij is equal to 0 for all j. Right? That's what it's saying. I mean, this is basically saying that the different columns are not linearly independent of each other. I mean, so you have the first column, so the first column here, second column there, and so on in this matrix M, right? And we are saying that, I mean, the fact that determinant is 0 means that these are not linearly independent of each other, right? That means there must exist some non-trivial Ci's, I mean non-trivial, which means not all the Ci's are 0, such that linear combination of these vectors is equal to 0 with those coefficients Ci, right? That's what. Okay, but now let us look at this specific form here. What this is saying, this means that J summed over Ci I going from 1 to n, so there is a summation here, I going from 1 to n. This is equal to 0 for all j. I mean, when you say this is that no? Sorry, this is probably saying no. This is a row. I'm thinking of row. So this is a row here. Row. So I'm taking linear combination of the rows. First row, second row, nth row, and we are saying that sum of these linear combinations is 0. So that should be true. I mean, it's a vector statement. So it should be true for each component here, right? So that's why it should be true for all j. Okay. So what does it mean then? So we are saying that this must be 0 for all j. Well, this is some vector, right? This is some vector in the after it's just linear combination of the basis vectors. Let's call this vector C. C is the definition is simply Ci I summed over I, right? And the fact that not is a non-trivial Ci's implies that this is not a null vector. This is not null vector. Correct? Because not all the Ci's are 0. So therefore, this is certainly not a 0 vector, not a null vector. So we are saying that there is some non-null vector whose scalar product with each j is 0. Okay. So in particular, if you take the C with C, right? What is C with C? Is nothing else but C. Take the dual of C, which is I mean, if C is this, the dual of C is what? The dual of C is C bar j, and the dual of j, right? Summed over j. This with C. Let's consider this. But we said that C with j is 0 for every j. So this is 0 because each term here is 0. No matter what these coefficients are, this term is 0. That's what it's saying, right? I mean, I just said C is that. So this equation can be rewritten as j, C is 0 for all j, right? This equation is that. This implies in particular that the norm square of C is 0. But that is we remember that one of the axioms of the scalar, one of the defining conditions of the scalar product was that the norm square of any non-null vector cannot be 0. It's strictly positive. So this is a contradiction. So we are saying therefore that the determinant of m cannot be equal to 0. Okay. Is that clear? This is a contradiction. Okay. Why? Because we are saying that the C is this is not a null vector. If it was a null vector, this is fine, no? But we are saying this is not a null vector. And why we are saying it's not a null vector? Because of this thing that we are saying there's a linearly dependent. These vectors are linearly dependent, right? So there must exist some non-trivial C's, right? Such that this is true, right? So this is not a null vector. But then there's a contradiction, which basically, I mean, you can invert it. I mean, this would imply that, okay, no, this is already this contradiction. So therefore, this implies determinant of m is not equal to 0, right? And then m inverse exists, so there's a solution. So it's a one-to-one correspondence. I mean, this will determine all these a bars. If you give me some numbers here, it will determine some specific a bars. Once you know the a bars, you know the complex conjugation of that will give you the a's, and that defines to you the vector. So, because that gives you a linear combination. I mean, so it's a isomorphic. I mean, okay. Now what else I can say here? Now see this. Scalar tensor, change of basis. Fine. So let's continue with now. So far, I mean, in the general case, we discussed all this. I mean, before we discussed the finite dimensional case, I mean, the previous lecture, we defined the various types of matrices, right? We defined A inverse if it exists, left inverse, right inverse. But here you see, for the finite dimensional case, is always true. Left inverse is equal to right inverse, and therefore it's unique. Inverse is unique. Finite dimensional cases. Then what else? Yeah, we defined the notion of the adjoint and so on, right? adjoint, Hermitian, etc. So let us try to write it. Since in the finite dimensional cases, we know that every linear operator is the same as some matrix, n by n matrix. Right? So can we understand the notion of, what is adjoint, what is a Hermitian matrix, it's a unitary matrix, etc., unitary operators, etc. So let's discuss that. It turns out that to get simple formulas, it is better to choose not an arbitrary basis, i's, but an orthonormal basis. Okay? It turns out it's much easier. Just to indicate to you why that is the case, let's look at just the adjoint, definition of adjoint, right? So adjoint was defined like the following. A dagger I j, or in general any a b for arbitrary a b was equal to a b complex conjugate, right? This was the definition of the adjoint operator. Right? So in particular, let's look at after all, now for the finite dimensional cases, we can express A in terms of matrices, right? So matrices means that I have to look at how A acts on the basis vectors, right? Whatever the basis vector you have chosen, right? Because you remember the matrix was defined like this. This was the sum AJI J, right? So the matrix corresponding to A was defined by studying its action on whatever basis you have chosen, right? Okay. So let's in particular look at this object. So we want to look at J, A dagger, I. Let us see what is this object. Well, this object is nothing else, but by this definition, you have to exchange I, A, J, and then take the complex conjugate. But A with J, A acting on J is simply A K J K summed over K, and here you have I, and then I have to take the complex conjugate of that. Similarly, whatever this object is, so this is the right hand side. Left hand side again, it will define to me what are the matrix elements. So this will be A dagger, I don't know, let's say K, I, K, right? This will be a definition, the matrix corresponding to this, whatever this operator is. And then I look at the J, summed over K again. Summed over K. So this is the left hand side, that's the right hand side. Let's further simplify this. So this gives you A dagger. These are numbers, so I can take it out. So K, A adjoint, A adjoint, Ki, and then Jk, right? Which is what I was calling, what was I calling? I was calling it Mkj, right? With this notation. Actually, it is, I don't know why I use the M. Let me use the G, okay? Let me use the symbol G for a definite reason. Actually, this is a metric. G is the usual symbol for the metric, okay? So let me use the symbol G. So this is G. Okay, so the left hand side therefore is simply A dagger, A adjoint. I shouldn't use the word dagger. A adjoint Ki, and then Gkj. Right? Okay. Actually, in fact, let me define, so to be able to write, okay, let me define the G. Okay, let's define, so forget this, let's leave it as it is. This was in the proof of the previous statement. Let me just define Jk is equal to Gjk. Let me define it like that. And even better still, let me put the index, one index up, other index down, Gk, to keep track of the covariant and contravariant. So this left hand side is simply Gjk A dagger Ki. This is a square matrix. I mean, this is some square matrix. I'm just labeling them. So J is the row, K is the column. And this is K is the row, and I is the column. So I can write it as a matrix multiplication. That's the reason I'm doing it. What about the right-hand side? Right-hand side, on the other hand, is, again, use the linearity property. So AKJ comes out. So you have AKJ. And then you have IK, which was by definition we said GIK. Okay. Then I have to take the complex conjugate of this. Right? That's the left-hand side. So now in the matrix notation, I can write it in the following. So remember, this is the row column. Row column. So this is the matrix multiplication G times A dagger. That is equal to, now notice that here J was the row, I was the column. Here you have I is the row, J is the column. So I have to take the transpose of it, right? Because if I want to exchange row and column, I have to take a transpose. Transpose is by definition that when you exchange row and column. So as a matrix equation, what we are finding is this is same as G A complex conjugate and transpose. I don't know, what shall I call it? Transpose. Transpose. This is transpose. So I take this matrix, take the complex conjugate, and then I have to exchange row and column, because here J refers to the row and K refers to the column. Okay. So okay, this is the equation we get. Well, so it's not, you see, because of this G, this equation is, the adjoint matrix is not simply the usual, for the matrix you have a notion of taking adjoint, right, which is simply taking the complex conjugate and transpose. If G was not there, suppose G was identity, suppose G was identity matrix, okay, in that case this would be the standard definition. What we are saying in the adjoint operator A, the matrix for the adjoint operator is the same as the original. Take the matrix for the original operator, take the complex conjugate of it, and then take the transpose of it. Right? This is the usual definition of dagger operation. Right? So that is why if G was proportional to G was equal to identity matrix, the expressions become much easier. Right? But if G is identity matrix, what does it mean? I mean, remember what was the definition of G? I erased it. I erased it anyway. Yeah, here, sorry, here. This was the definition of G. If you are saying that this identity matrix, that means this is orthogonal basis, right? So if you had chosen orthogonal basis, all these expressions become much easier, in the matrix. Although not necessary. I mean, you can work even if there is a non-trivial G, non-identity G, still you can work with it. I mean, there's no problem. But it just that this G keeps hanging around everywhere. So that's why it is convenient to go to the orthonormal basis. Yeah. So well, let's go to the orthonormal basis. I should stop soon. Okay, so given any basis, there is this Graham-Schmidt procedure to go to the orthonormal basis. It always exists. I mean, you can always systematically construct. It may take a long time if n is large. It may take a long time to explicitly construct the orthonormal basis, but we are guaranteed it exists. You can construct it. Huh? So we can. So from the basis I, you can always go to the basis, which I will always denote it by EI. Whenever I use orthonormal basis to distinguish between the two, I will use this symbol, EI. So this will be the orthonormal basis, which means that EI with EJ is delta IJ. That's the Kronecker delta. So in that case, the adjoint operator, A dagger. So you now write the matrix in this basis. Okay. In this basis, adjoint operator is simply what we say A bar transpose. So take the matrix of A, take the transpose and complex conjugate. And the Hermitian matrix, a Hermitian operator will give you simply the thing that the dagger is the same as original matrix. which is the usual thing that you are familiar with, right? That is why I said it's convenient to use the orthonormal basis. There everything becomes simple. So this is the adjoint, and Hermitian means A bar transpose is equal to A. Similarly, unitary means that A bar transpose is the inverse of the matrix, unitary matrix, and so on. So now, but I should just mention here that you see, when I change the basis, I mean, the things we said about the A inverse exists means determinant of A is not 0 and so on. I mean, you may wonder what happens if I change the basis, will the determinant change? Right? But any change of basis, you remember under change of basis, with the matrix A, so under a change of basis, so where I prime is R, I, J, this matrix R, again think of so matrix R whose components jth row and ith column is this number. Then matrix A transforms to, A prime, the new matrix is R inverse AR, matrix multiplication. So the question is, so what is let's look at the determinant of A prime. Well, that's the same as determinant of R inverse AR, which by using the product rule, determinants, this is simply determinant of R inverse, determinant of A, and determinant of R. Now combine these two things together, that's the same as determinant of R inverse R times determinant of A, but this is identity matrix, so this is 1, so we see that this is same as determinant of A. So the important property is that determinant of A doesn't change even when you change the basis. Okay? So this is such quantities which do not transform under a change of basis are called scalar quantities. This is a scalar. It's invariant under a change of basis, right? Scalar object. Actually, there's another scalar you can construct from the matrix A, and that's a trace of the matrix. So if you take the trace of the matrix, trace of a matrix A, trace A, which is by definition simply A I summed over I. So you just take the, A has this A has a sum form. You're taking the trace. This was, remember, A1, 1, A1, 2, etc. A2, 1, A2, 2, and finally up to A and N. So what this means is just take the diagonal and just add the diagonals up. That is what it is. This is also invariant. Why? Because trace of A prime is simply equal to trace of R inverse AR, and I don't know if you're familiar with this. Inside the trace, you can cyclically move around the matrices. I don't know if you're familiar with that. Okay, let's prove this explicitly. So what is this? This by definition is R inverse IJ, AJK, and RKI, right? This product of matrices, if I look at the ith row and some say lth element, it would be simply this, with this being L. But finally, I have to identify the two and add them up to compute the trace, right? So that's what it is. But now you can put this R here. You see this is RKI, R inverse IJ. These are numbers. I can move them around. AJK. But now look at this part here, summed over I. That is simply the component of kth and jth component of R times R inverse. But that's identity. So that's delta Kj, Kronecker delta. So this is delta Kj times AJK, which is the same as AJJ. Summed over. All the repeated indices summed over. So you see a trace of A prime is the same as trace of A. This is a general property. This is important to remember this. This comes many times. If you have inside the trace, you have product of several matrices, you can cyclically move the matrix around. Only cyclically. In general, if I take a trace of say products A, B, C, D, E, etc., several matrices here, right? Then I can, this is the same as trace of say B, C, D, E, A. You see, you move the A around, you can move around cyclically. That this is an important property of the trace. So if you knew this property, then it's immediately obvious, right? You just move R here, at R times R inverse is identity. So these are two independent, two scalar quantities, because they don't, even changing the basis doesn't change. This is useful things to remember. Okay, so in particular, going from some basis to an orthonormal basis is again a transformation. Under this transformation, determinant of A doesn't change. So if something had an inverse in the original thing, also it has an inverse in the orthonormal basis. Okay, maybe I should stop now because it's getting late. Yeah, okay, we'll stop here now.